In this video, I'm going to describe and prove some properties of the centroid of a triangle. The centroid is defined as the point where all three medians of the triangle intersect, and a median is the line that connects a vertex to the midpoint of the opposite side. For example, vertex A connects to the midpoint D of the opposite side BC. In this triangle, all three medians intersect at point O. So O is the centroid of the triangle. These are the properties that we are going to prove for the centroid of a triangle. The first one says that the centroid divides the triangle into three triangles of equal area when the centroid is connected to each of the vertices. In other words, these three colored areas here are equal in size. So the light blue area is equal to the size of the dark blue area, which is equal to the size of the gray area. The second property says that the three medians intersect at the same point. Two medians will intersect at a point. The third median will also pass through the same point. The third property is saying that the centroid divides each median into two segments in a 2:1 ratio. So in this example, the lengths of AO and OD are in the ratio 2:1. The last property that we're going to prove is that the coordinates of the centroid are given by x1 plus x2 plus x3 by 3, y1 plus y2 plus y3 by 3, where x1, y1 are the coordinates of A, x2, y2 of B, etc. In other words, the centroid's coordinates are the average of the coordinates of the three vertices. Let's look at some properties of the median of a triangle first. In this example, D is the midpoint of BC and AD is the median that connects A to the midpoint of BC. The claim is that the area of triangle ABD will be the same as the area of triangle ADC. If this is obvious to you, you can skip over this section. First, I'm going to extend line BC and drop a perpendicular from point A to represent the height of the triangle. The base of triangle ABD I'm going to mark as B. Area of triangle ABD will be half times B times H. Now DC is the same length as BD because D is the midpoint of BC. So the length is the same, B. Also the height of triangle ADC is also H. So the area will be half times B times H. So both triangles have the same area. Also, if you look at the area of triangle ABC, this will be half times base, which is BC, times H, which is equal to half times 2B times H, or B times H. So the area of triangle ABC is twice the area of ABD and ADC. In other words, the median divides the triangle into two halves of equal area. We'll use this result in the next proof. Let's look at the first property of the centroid that we want to prove. In this triangle ABC, there are two medians, AD and BE, and they intersect at point O. I'm going to connect O and C with a line segment, but I'm not going to assume that this is a median. We still have to prove that all three medians pass through the same point. The property we are interested in proving is that the point O, when connected to the three vertices, gives three triangles of the same area. So for this example, we want to prove that the area of triangle AOB is the same as the area of triangle BOC, and that is the same as the area of triangle AOC. The first thing to note here is when we look at triangle BOC, OD is the median of this triangle. The two triangles that are created by the median OD are of equal area. And the same thing applies for triangle AOC and median OE. The two purple triangles have the same area. I'm going to call that area X. And the two blue triangles have the same area, which I'm going to call Y. Area of triangle AOB is Z, and we want to prove that Z is equal to area of triangle AOC, which is 2Y, and also equal to area of triangle BOC, which is 2X. Now if you look at triangle ABC as a whole, AD is a median, so which means that the area of triangle ABD is the same as the area of triangle ADC. We can see that area of ABD with our nomenclature is Z plus X, and the area of triangle ADC is 2Y plus X. So cancelling out X from both sides, we get Z is 2Y. And this is the first part of the statement we wanted to prove. Now similarly, if you look at the other median BE, it also divides the triangle into two equal halves. So area of triangle ABE is equal to area of triangle CBE. So ABE is Z plus Y and CBE is equal to 2x plus y. And again, we can cancel y from both sides and we end up with z is equal to 2x. So we have proved the statement z is 2y is equal to 2x. And since 2y is equal to 2x, x equal to y, so which means that all four of these colored in triangles are actually the same area. Z, 2y and 2x each represent 1/3 of the total area of triangle ABC because they are all equal partitions. And that further means that x and y are 1/6 of the area of triangle ABC. What we have proven so far is that the point of intersection of any two medians of the triangle creates three triangles of equal area. In the next section, we will use this fact to prove that the third median will also pass through the point of intersection of the other two medians. The next property we are going to prove is that all three medians intersect at the same point. To prove this, let's start with the original triangle. We previously proved that for triangle ABC, if we choose any two medians, in this case median AD and BE, their point of intersection O divides the triangle into three equal area partitions. And as we saw, these purple areas marked in X are all of the same size, and X represents 1/6 area of triangle ABC. Now this result holds for any two medians of the triangle. In this case, the medians were AD and BE intersecting at O. The same result holds for the third median CF and its intersection with median AD. These two intersect at point Q, and again, all the triangles shown in blue have the same area X. X is 1/6 of the area of triangle ABC. So in this proof, we have to show that point O is the same as point Q. If that's the case, it means that CF passes through O and all three medians intersect at the same point. Let's go back to the original two medians intersecting at point O. As we saw, the area in purple has size X. Now I'm going to connect C to the midpoint of AB. What I'm assuming here is that Q, which is the point of intersection of AD and CF, is different from O. In other words, the median CF is not passing through O. Now, if we look at the picture on the top right, which showed the intersection of the medians AD and CF, the area of triangle DQC was also X. So if we overlap the two triangle areas, DQC and DOC, we see that both areas are X. This is clearly impossible as long as Q and O are different points. So our assumption that Q and O are different is wrong. And that means that median CF has to pass through point O. So we have been able to prove that all three medians must intersect at the same point. The next property that we're going to prove is that the centroid divides each median into two segments in a 2:1 ratio. Again, I'm going to use the same picture as before. Triangle ABC with two medians AD and BE. Triangle ABO, which is this triangle, has area 2x, and triangle BOD, which is a smaller triangle next to it, has area x. These triangles share the same height. I'm going to draw this height in red here. Area of triangle ABO will be half times the length of AO times h, and the area of triangle BOD will be half times the length of OD times the same height h. We know that the areas are in the ratio 2 to 1. So what we get is half times AO times h is twice half times OD times h. And then cancelling out the common terms on both sides, we get the length of AO is twice the length of OD, which is what we wanted to prove. To summarize briefly, since the two triangles share the same height and we know that their areas are in the ratio 2 to 1, it's obvious that the base lengths also have to be in the ratio 2 to 1. Next, we are going to find the coordinates of the centroid in terms of the coordinates of the three vertices of the triangle. I have marked the coordinates of A as x1, y1, B as x2, y2, C as x3, y3. From the previous theorem that we proved, the ratio of the lengths of segment AO and OD is 2 to 1. So I have marked the length of AO to be 2 times L and the length of OD to be L. So now we need to find the coordinates of O. To find those, first we're going to find the coordinates of D. D is the midpoint of BC. So the coordinates of D will simply be the average of the coordinates of B and C. The coordinates are x2 plus x3 by 2 and y2 plus y3 by 2. Now to find the coordinates of O, we are going to use the coordinates of D. Point O is dividing the line AD in the ratio 2:1. In general, if you have a line segment MN and a point O that divides that segment in the ratio dm to dn, how do we find the coordinates of O? Similar to the midpoint, the coordinates of O in this case are a weighted sum of the coordinates of M and N. But what are the weights in that case? In this example, we can see that point M is closer to O, so it should have more influence on the coordinates of O. It turns out that the weight for the coordinates of M is given by the ratio dn divided by dm plus dn. In this case, dn is larger than dm. xm should have a larger contribution to the coordinates of O, so it makes sense that dn gets multiplied by xm. So we can write the x coordinate of O as dn divided by dm plus dn times xm plus dm divided by dm plus dn times xn. And the y coordinate has a similar form. So going back to the triangle, O is closer to D than it is to A. So it makes sense that D will contribute more to the coordinate of O. The x coordinate of O will be given by 2/3 the x coordinate of D, which is x2 plus x3 by 2. And then A will contribute 1/3 x1. So if we simplify this expression, we will get x1 plus x2 plus x3 divided by 3. Similar process for coordinate y gives y1 plus y2 plus y3 divided by 3. So the coordinates of the centroid of a triangle are given by these formulas.